Software data processing, and we're going to start off with
Okay, thank you. Good afternoon, everyone. I'm Yongkun from NOC, and today I will talk about software for fast read burst. And the title is From Single Pass Search to Deep Learning Discovery. So I will first review classical single pass search, and then I will move to GPU pipelines and AI. After that, I will show our fast work, drafts for search, and after for analysis and anomaly detection to find unknown signals. So let's start with the first FRB, the Lorimer burst. Parks recorded it in 2001, and it was discovered in archival data in 2007. The signal has been sitting in the data for about 6 years. This raises a simple question. The signal was very bright. In principle, it should be very easy to see. Why didn't we find it earlier? So in a blind search, the true DM is unknown. So to find a burst with an unknown DM, we have to try many DM values. For each trial, we disperse, run match filter, and set a threshold. The cost grows with the number of channels, the number of time samples, and the number of DM trials. And older computers cannot handle this. And by the mid 2000, CPU become faster and the storage become cheaper. So high DM search finally become practical. So the first FRB teach us discovery depend on sensitivity. It also depend on computing. And better computing open more of FRB parameter space. So this slide shows the classical pipeline. It comes from pulsar search. There are 5 steps. First, clean RFI. Second, disperse over a grid of DM values and transform the raw data to a time series. Then run a match filter at different widths and find the signal peaks. First, cluster those peaks into candidates, and finally classify each candidate as real or not. And this method is reliable. Every step has a clear physical meaning. For this reason, most search workflows are built on these steps. And later tools mainly improve speed and adapt the workflow to different telescopes or different data formats. And over the past 2 decades, this core loop was built into many different search. And Presto is a reference CPU toolkit from 2001, and Hamidol moved the dispersion and the matched filtering in GPUs. And Cham used Bonsai, a tree-based dispersion method that had over 1,000 beams at once. And Transient X is a modern implementation for high-performance single-pass search. And RealFast is the image plane case. It searches VLBI data and can localize the burst. And these tools have different designs, but they share the same concept: try DMs, disperse, filter, and make candidates. So as the search become faster, the largest cost move to filtering. Wide field and many beam telescopes can run with high duty cycle. The data rate can reach terabytes per hour, and search pipelines can produce a huge number of candidates. And most candidates are RFI. After clustering, many candidates still remain. A small fraction is used for human review, and a smaller fraction becomes a real signal. Sorry. So a Cham example on FRB 2022-0912A shows this clearly. There are nearly 30,000 events over threshold, and only 800 are true FRB bursts. Sorry. So the bottleneck has changed. Earlier, it was hard to find anything. Now, it finds too many signals, so we need to extract the true signal from many false signals. So this is where CNN classifier become useful. And a well-known example is fetch. It reads the frequency time image and the DM time image of each candidate. Then it decides whether the candidate is a real FRB or RFI. And this reduces the load of human reviewers. But this is just a plugin after classical pipeline. And Presto or Hamido still has to run first to generate the candidate image. And earlier missed signals still missed. So this motivate a more end-to-end solution. And each classical step can create extra cost. RFI cleaning can create artifacts, and the dispersion is expensive. Match filtering repeats many calculations, and the same burst can appear many times at nearby VMs. And the final candidate still needs a lot of human checking. So we create drafts. We treat FRB search as a computer vision task. The model looks for the bow-tie structure in the DM time map, and then a classifier checks the dynamic spectrum. So this gives an efficient end-to-end pipeline, and I will describe it in detail later. And there is also a more radical direction. Remove the full dispersion loop and search directly on the raw spectrum. This can save more time. Here we list some tools. Raspdam, the multi-beam efficient net, FRT search, and SwimVanNet are all moving in this direction. They recognize or segment the dispersion curve directly in the time frequency image. Then they infer the parameter from its shape. And the advantage is speed. One pass inference can avoid a large DM loop and reduce duplicate candidates. And the main risk appears in blind search. A large unknown DM range requires a wide input window. For weak burst, noise can dominate the input before the dispersion curve before visible. So this slide puts the detection inside a full FRB system. And after a burst is found, the system has to alert it, and it may also save baseband or voltage data. Then it has to localize the event. After that, follow-up observations connect the burst to a host galaxy and environment. So FRB software has to connect the real-time search with physical interpretation. Now I will move to the second part. I will talk about our software and AI work for FRBs, and after we find we find a burst, then how to measure it. So first, the search. We built a draft, which is short for deep learning radio fast transient search. And in this pipeline, the GPU first turns the data stream into a DM time image. And then an object detection model finds the burst arrival time and the DM value. Use this location, drafts cut the corresponding signal from the raw data. And a classifier then checks whether the candidate is a true burst or not. And the direct localization on the time DM map reduces the duplicate candidates. And because everything runs on GPU, the dispersion plus inference is faster than the data arrival rate. One consumer GPU is enough to run it in real time. And this slide shows the actual search process. And the left animation starts from the raw frequency time data stream. And the middle animation shows what drafts produced from this stream. And the data are converted into a DM time search map. Okay, then detect a box on the map, and each box marks a possible burst. Then the matching dynamic spectrum is sent to the classifier. And we test the performance on a real fast data set. We compare the drafts with Presto. And to process on 1 6-second file, Presto takes about 1,200 seconds, and drafts takes only 6 seconds. This is roughly 200 times faster. And for precision, Presto drops below 9.6% and low threshold, and drafts stay at 99.8%. And for recall, appraisal is between 79 and 87%, and drafts reach nearly 100%. So this is exactly what a survey needs: the speed, completeness, and a manageable candidate list. So next is the next is a real data set. So we apply drafts on a repeating source FRB 2019-0520B, and we researched 18 hours of fast data, and the original Hamilton search found 75 bursts, and drafts recovered all these 75 bursts, and it also found 183 new bursts. So a large burst sample change later analysis. It affects the energy distribution, waiting time distribution, and active rate. So once the burst is found, the next step is measurement. This slide lists common open tools in FRB field. So YOR and SIGPy handle reading the data, and DM face refine the DM, and fit burst fits the shape of the burst. And RM tools handle polarization and FRB rotation and path. Models to estimate the distance. And with the standard tools, we can produce unified outputs and compare results across observations. In our pipeline, we made a fast So it uses AI to automate most of the data processing workflow. You give it raw face data. It first runs a draft search to find the time and DM of each burst. Then it cut out the burst segment. Then it calibrates flux and polarization and locate each burst. Finally, it runs burst analysis and produce tables, plots, and a dashboard. With after, the interaction can be very simple. You can tell the agent, here are the data, then it will give you the result. And this greatly improved our data processing efficiency. It also makes the results reproducible and comparable across observations, which is very important for later science. And this is a dashboard. This is a dashboard that after generate from a real observation of FRB 2022-09-12A, and this one observation recorded 32 bursts. And from this dashboard, you can see almost all basic information from this observation. And this is the other half of the STEAM dashboard. It shows the polarization, the dynamic spectrum, arm distribution, and the detailed burst catalog. So after drafts find the candidates, after automate the full analysis workflow, this greatly lowers the barrier for data processing, and anyone can process the data independently, and the output can be compared across studies. And after we automated the full FRB data workflow, we started to think a broader question. And most search pipelines start from a known signal model. For FRBs, we search for the dispersed single pulse. And for pulsar, we search for periodic signals. And observing data can dispersion speed, and some have how to name. So we need anomaly detection. It looks for signals that differ from known classes. So we can inspect those examples and decide what they are. And we should also note one point, and a new signal can mean more than one interesting event. It can open a new field. FRB is a good example. So the first step is to learn representation. The radio dynamics and it has time on one axis and frequency on the other. This makes audio spectrogram transformer a useful starting model. We pass each dynamic spectrum through the AST encoder and obtain an embedding. Then we use LoRa for small data adaptation. This updates only a small number of parameters. And after that, we compress the embedding with PCA and use TSNE to visualize. This work is mainly done by Jayanta from AOC. And the training class are routing fast signals, background noise, pulsars, calibration noise, and fast dynamic spectrum. After training, we place ADLEO, a stellar example, into the same embedding space. And they form a separate group away from the routing classes. And then we trace an outlier back to the original dynamic spectrum. The spectrum shows the stellar flare structure. So putting this piece together, I think there is a fourth step for AI in radio transient. The first level is triage. A network decided whether a candidate is an FRB or FI, and fetch and draft classifier are examples. And the second level is automation. A workflow runs from raw data to measured parameters. This is the role of drafts and plus after. And the third level is discovery. A foundation model embedding space can surface signal before a predefined template exists. This is the role of the AST for anomaly detection. And the fourth level is reasoning agent. In the future, agent can plan observations, call tools, and test hypotheses. So this is my talk. Everyone can find the drafts and after in my GitHub. Thank you. Which is software? Yeah, anomaly detection.
How people define the dispersive curve for find anything, including that in the image.
We hope it can find anything exclude the training data set. For now, we trained the model using the dispersion curve, some pulsars with single pulse and noise and calibration noise. So we hope to find any new signals rather exclude the class. For example, lightning or some RFI we never seen, or some the radiation from stellar, or maybe some new signals. We don't know.
Made by AI.
Sorry?
Your slides are really cool. Are they made by AI?
We don't know. We are still in try. We're still trying.
Research models, software analysis, knowing that the software generally go to the lawyer, not about.
Sorry, I kind of hear it clearly.
Can you use this draft software on molecular skills?
Right. We trained the drafts on using fast data, but we also applied drafts on GPT observation. It also works well. You can find some paper cite drafts for FRB search.
Okay, I think we'll pass it to the there. So yeah, lots of making discuss.
Okay.
Yeah, I'll take it again.
So the open document doesn't work? Does it work? Oh yeah, installed. Excellent, thank you. Stuff.
Right. Cool. All right. Thanks a lot for having me. Yeah, I'll speak a little bit about our VLBI campaign called Precise. And mostly this is about characterizing local environments. There's a bit of a spoiler. Not many new local environments to discuss today, but still we'll go through it. And a lot of this work is actually done by people in the Astrophysics Exploration. Probably acknowledge that because most of the students and postdocs in that group are doing all the hard work. I'm just organizing the observations. So let's start off with why we do this. So of course, we all want to understand FRBs, and there's different ways of looking at them. Of course, topology, time frequency evolution, polarization. You can look at the host galaxies. You want to look at population studies. You can do all sorts of things. And what we do in this particular project here is that let's see what the other plots are going to look like. Maybe we can go back to the PDF because this is not going to work. I think there's lots of stuffed up. Sorry. That's what happens when you go from one LibreOffice version to another. I'm sorry. I had a little GIF in there, that's all. We can just go to the PDF, forget about the GIF. Sorry. I shouldn't do this though. Anyway, so what we're doing is linear second localization of FRBs, and the point there is that just the host of the FRB isn't necessarily enough. So what we do is actually zoom in on the linear second levels and actually compare the linear second resolution and plotting of data. So things like JWST, Hubble actually have a comparative resolution in the optical, and which then actually helps you fix it up, which then helps you to gives you a clue on what the actual local environment of the FRB might look like. So is there a star forming region? Is there none? Is there a persistent radio, a compact persistent radio source, a PRS, are coincident with the location of the FRB? And this is stuff that you can mostly only do with VLBI. And this is what we do. We're running this lovely project called Precise, stands for pinpointing repeating chime sources with the EVN. So initially we started with chime sources. These days we're following all of the known and new repeaters. We're an EVN-like project, where light means we're still using the full EVN. Well, you see some of the dishes we're using regularly, but only when there is a detection do we actually correlate the data. So most of the data actually goes in the bin. Only when we have a detection do we use the correlator. We get some 500 years per 500 hours per year. Mostly governed by the availability of Effelsberg. The Effelsberg dish is our detector because it's the most sensitive dish in the array. And we also have eMerlin in the array because eMerlin is actually great because it provides intermediate baseline, right? If you want to be sensitive to extended emission of where your FRB is, you need some shorter baselines, otherwise you resolve it all out. So what we do, the way this works is that we transfer all of those data from Effelsberg to Onsala Space Observatory, which is where I am. So this is my favorite dish. And if you don't know where Onsala is, so this is Northern Europe, this is Sweden, there's Oslo, Stockholm, and I'm here in Gothenburg. And we have our local pipeline, which then takes the baseband data because we actually observe in VLBI mode, so which is using regular VDIF, regular baseband data. This is then transformed to filter bank using your regular pulsar tools, DSPSR and SIGPROC. And then we use Heimdall and Fetch to find and classify. And I already learned today there's newer tools, drafts and whatnot to actually do the classification. We might find way more. Oof, gee. So what we've done since 2019 is sort of summarized in here. Overall, we've targeted some 64 different repeaters by this point. Some of them we obviously observe more often than others. One of our favorite ones here is probably R4, which is, I forgot the actual name, but I think some people know what, well, R4, the fourth repeater. Anyway, we spent a lot of time on this source, but it doesn't seem to like us in L-band. But we have localized roughly 9 of the repeaters at this point. Some of them were very easy. For instance, this one here, I think it's R177 or whatever. And there you just sometimes need 1 observation or 2, you get 100 bursts and you're done. Others, we spent hours on end and didn't have any detection. In total, at this point, we've spent roughly 3,000 hours with this array, and this is quite a substantial fraction of what the VLBI network typically does. So in terms of latest results, so we had this lovely paper by Dante Hewitt, which was on 2019-0208A, which is to me, it's number 12. Here we had just a single burst, so we spent some 16 hours on source burst, and the issue is that, of course, with just a millisecond of data in a VLBI array, you cannot really use Earth rotational synthesis. So you have these really unhappy beams. And in this particular case, because we got Effelsberg in the array, there is one east-west baseline, one north-south baseline that sort of dominate the array. You get this nice cross pattern with all the different side lobes, and what you can then do, you are just very brave and you fit Gaussian to this distribution of side lobes, and you can actually manage to localize the source. In this case, it's not too impressive, 260 by 260 milliarc seconds, so the Chinese clip already knew better these days, seconds, but still, you need this sort of resolution to then, in the end, localize the source to this little smudge here, which initially we did not find any host at all, but then there was spare time on the optical telescope, and they just spent a couple more hours on the target, and then in the end it was, a 27.3 magnitude R-band host there at this very location. So we don't have a redshift yet because it's a bit too faint, but it's at most 0.83, somewhere in between. And we have not seen any compact radio source at L-band to this level. Now, not too long ago, Mohit Babaj and Mark Snellis published this little paper on 240114A. We already had 2 talks on the source, also one of the hyperactive sources, which for a while crazy. And this one turns out is actually in an SMC-like satellite galaxy of a more massive host. So it's the first FRB actually localized to a pair. Right? Most of the, as of yet, localized sources were sort of in non-gravitationally bound pair-like systems. This one is the first of them. It's a star-forming dwarf galaxy, stellar mass of about 10 to the 9 solar masses, redshift 0.13. There is evidence for a persistent radio source of 5 gigahertz. We didn't see anything in L-band, but there is some evidence for it. And just earlier today, we saw that there is also a very little rotation measure on this particular source. So it's another one of these hyperactive repeaters that also has very low error. Now, on Archive, you can actually also find our latest oscillation of our own. The very first repeater, what we did here was to actually go back and see if we can improve the co-location between TRS and the FRB, because there was some 40 parsec, 40 parsec accuracy on the localization of today from Benny to Makulta at 5 gigahertz, and of course you can then ask, okay, how far can we go to actually prove that these are co-located? And what you see here on the right is one of these lovely examples of when you have multiple bursts that you need to be really careful how you do your astrometry, because depending on which of the bursts you actually take and how you combine them, and whether you use, so the blue cross here, so there is a pale one and there's a solid one. The pale cross is actually the C-band localization of the PRS using the International Select Reference Frame. from the time when these data were taken, when this paper was published. But since then, the phase reference source, the position of the phase reference source has been updated. And we're talking, about a milliarc second, but the milliarc second makes a difference. So this shifts the position in this frame further up here, which is then very, very close to the PRS L band. And we actually managed to, so at 1.4 gigahertz, managed to actually localize the source down to an accuracy of 10 parsec, which I think is brilliant. And on top of that, and we've seen a similar thing earlier today, Mark also showed that there is this trend of a decreasing DM and R1 over time. So, and this is actually data from Marseille that sort of showed this downdrift, or this reduction in DM. Oh yeah, this is what the GIF was meant to be, because I wanted to show a little bit of the rotation synthesis, because the more best you had. So here it looks horrible, right? They all slide up, so can't really do much of what it is. And it actually meant to show that, you add one burst, then it becomes just one dot. But you just have to believe me that this is true. This is work done by Alex Moroniano. This is the source that gave us a little pain because it took a long time to actually localize it because our models were wrong. But in the end, we managed to localize it down to some 5 by 3 milliarc second accuracy. The position of the PRS, it's another one of these sources with a persistent radio source, coincides with a VLA detection of a persistent source in the region by Yongkun et al. And lo and behold, they actually agree. This is one of those FRBs, well, for us, it's the highest DM FRB that we ever localized, 1300. And since the line of sight is pretty clean, it would seem that the host contribution is actually quite high at 1200 parsec per cube centimeter. Also here, another one of those sources with a variable RM, so it actually went down by 1,000 units within 50 days. And it seems to be sort of similar to R1 and the R1 twin. So, there's some trend going on here. And this is something that has not yet been published. This is R6, which is actually somewhat of a forgiven child, because this is actually the very first FRB we ever detected with precise. So this predates the global cluster FRB, because the global cluster FRB was then more exciting, so we did this one. But finally, somebody's working on these data for R6. We've localized it. You see another cross pattern here. This is actually 4 bursts, but the frequency coverage here wasn't great. So this is why we also have some side loop ambiguity. It's in a low star formation rate galaxy. It's a composite galaxy, somewhat elliptical. So it's somewhat atypical. It's not quite the low star formation dwarf galaxy type thing. And at this point, we still don't have a persistent radio source for this one. Which brings me to my very brief conclusion, really. One can say that there is some trend that those hyperactive repeaters, quite a few of them have a PRS, and quite a few of them do show variable R and variable DM. And so the question is, you could argue that there is maybe some evolution, age-related evolution of these sources. If these were young and they're born in a dense environment, which then, there's lots of magnetonic activity going on. But then to prove this, you need to monitor them for a long time. Question is for how long? R1 we've been monitoring for about 10 years, 15 years. We see some evolution, so let's see what time brings. And then, of course, in the end, technical FRBs is still hard. RFL doesn't get better. And then precise with quite desperate at this point, because we haven't had a detection in 1.5 years. So fingers crossed, the universe becomes more kind to us again. Thanks a lot.
Yeah.
Okay, well, so you asked about the 240114A, whether there was a PRS within the question. Yeah. We didn't count them. Yeah, so I think that there was a hint for PRS at C level, right? But there doesn't seem anything at all. I think you mentioned that we say that's all then consistently well that we feel that compel them was
I think that's not the way we say offline. It's about when did you not detect it? Oh, okay, so I think yeah, let's just have a line. And we have one further question. And we'll get the okay.
No.
This one, right? This is all changed now. I don't know where that is. Okay. So you can, so each verse, right? So the type of the verse is always different. So you always have some of the different meaning. And then you have breaking verse, you have plaintive verse, and then depending on how you combine. So this is just, oh, okay. So you see that we're combining 3, 4, 3 verse, we're excluding one verse because there was somewhat funky or something wrong with it. And this is just what I mean, where you have to be really careful that, you know, if you just have one verse, you're never going to say, okay, this is 10 million technologization because something is always funky. And the main point here being, be careful about our geometry. And it's just trying to be honest, right? We have, if we take this combination of verse, we can know that. If we take that combination of verse, we can know that. And we need to have really good arguments to say, but we're deciding on this location because this is the best for such and such reasons. And it's just trying to be honest. It matters what you do. That's all.
Let's say that once again. Speaker is Jayanta. Go ahead and combine. You know,
So I ran, can you hear me?
yeah,
Yeah, I just shared the screen. Yeah.
you and the other one, okay. And I will give you a warning at 10 minutes of the stream.
Yeah, sure. Thank you. Okay. Thank you, everybody. And actually, and thanks to the organizing committee for giving us the spotlight team the opportunity to talk about it. And very sorry that we can't make it, and really missing this exciting meeting. So you can see the team sitting here eagerly kind of listening to the talks and kind of learning. So, okay, so what we're going to talk about the Spotlight project at the GMRT. And so this is a new project which just started. So maybe one slide I'll just spend about GMRT because this could be the first talk which is using this telescope. So, and many of you have used GMRT successfully. So it is nothing new, but just to kind of go over the main point of the telescope. So it's operating from 100 megahertz to 1500 megahertz, and it is actually is an array of 45 dishes. 45 meter diameter 30 dishes and spread over it at 25-kilometer baselines, and recently is upgraded the bandwidth going all over 200 and 400 megahertz, and which makes GMRT an excellent instrument for time domain study as well as imaging study. And that's where this project Spotlight is coming in, because once the bandwidth upgradation happened, we thought of converting GMRT to a survey instrument in addition to be a good follow-up instrument. So this is a Spotlight project. As you can see, the teams are sitting here who are actually putting a lot of effort to get this thing online. And so all the faces, and some of them may be kind of getting connected to you looking for PhD and postdoc positions. And you can see this like the web pages there, but let's go to the project. So I'll straight away go to the main block diagram, and then I kind of expand the unique features of this project. So like, as you can see, as a like basic interferometer system, so we kind of capture the accurate sample data. So we have to have our own correlator and beam tiling, because it's very much similar to like mid-trap projects. So we'll form hundreds of beam on the sky. So we have a tiling system as well as correlated beamformer. And the beamformer is a little different, which I'll talk about why it is like that. And then we fed the data to 3 different backends. One is to do the real-time transient search, which will be mostly we'll be talking today. And in addition to that, there is a pulsar search, two pulsar search backend. One is using FFT, another is using FFA, fast folding algorithm for long period pulsars. And all this detection, which come mostly the detection which come from the transient search pipeline, which is the real-time detections. And then we actually go for the baseband dumping as well as the visibility imaging. So we trigger the imaging, real-time imaging at millisecond resolution, which is this pipeline talks about, called PICO. And then we have the detection from there goes to the discovery page, as well as it take up to a follow-up processing. So as you can see, just in terms of the how big the system is like hundreds of A100 GPU and large amount of memory, almost like a 2 petabyte per day you are basically processing. So we have a large amount of storage to kind of hold the immediate detections before you kind of classify immediate detection before you kind of sure whether they're really true or not. So just to kind of zoom in further on the transition pipeline, which is the kind of topic for today's discussion, is we have this two part, like I said, like conventional transient search pipeline, we have dispersion, single pulse search, and then finding out the peaks. And then we have the second part of that, which does the candidate reduction. So we're just filtering out some of this redundant candidate as well as the spurious candidate, and various kind of filtering, clustering. And then I'll mostly highlight these two part. One is this feature extraction. What is special about this one, and then how optimal this is, and then classification you are using fetch with some modification on that. So as you can see, there are two different kind of data product we have. One is the rapid science data product, which is kind of fully functional now, where you have a real-time detections followed by arc-minute localization using the beams, and then arc-second localization using the imaging, and then the quasi-real-time pulsar search. The second part of that, which is basically data-intensive pipeline, where you basically dump the baseband data and do the polarization calibration and spectro-temporal polarimetric study of that. That's kind of under development right now. So, but still, I'll show some result from that. So before we go to the kind of development path, so this is kind of where this project looks like. So it is so based on this our last few years of GMRT observation, because this is a commensal project, so we basically go in the GMRT and then fetch what GMRT has done over last few years. And based on that, we could see that what kind of detection possibility we have, and then this kind of circular bar diagram shows you a different frequency coverage of GMRTs, like all like very low frequency, and then mid frequency, and then the L band. And you can see, and then there are some region which is like just go to below 100 or below 200 megahertz, and just we don't cover those because we really struggle to kind of get rid of RFI, as well as our memory requirement is huge about this part, and so that part is kind of remaining, but rest of the thing we are covering. And from that, you can kind of see how much FRB, you can see like hundreds of FRB per year kind of number, and looking for a 3 years of funded projects, which is where the science operation is fully funded. And we see that the kind of median DM, because of the sensitivity of GMRT, you can push a little bit of median DM around 0.6 or something for the population which we expect. And there are like final aim is to get a 2000 beams, but I'll talk about what is right now happening. We also have we see one of the known LPT in the blind search from the Spotlight data, which was a till early this year. So some of the unique features, basically this, since it's interferometer, we had the visibility like what Frank has talked about, the EVN. So similarly, you have the real-time visibility at 1.3 millisecond resolution. And then the beam which we produce is actually using visibility, and that's kind of show here. So the left-hand side is a tied array beam, and right-hand side is the post-correlation beam. And as you can see that the beams are actually really clean, where you can both see dynamic spectrum and the DM transform nicely. So not only the temporal and spectral resolution, you also see in spatial resolution. So there's a beam is coming out from the phased array and the post-correlation. In the spatially also they are very clean. They have less side lobes, which really helps us to kind of localize the source in the beam level, because we have reduced confusion at this point. And then these are a kind of tiling of our system, and we kind of tested through putting sources at different off-axis region and kind of recovering them with the expected signal to noise ratio. So some of this test has been shown here. And then the one which actually we talked about, the candidates feature extraction, and where because since we go all the way up to 300 megahertz, we kind of found that it should be better placed if you optimize the candidate features based on its DM and its width and then frequency. That's what this diagram shows. So the lower panel is actually the code written by Ujjwal, and this is the candies, and then top panel is actually the same features that extracted by the EOR. And since you are actually optimized to the particular DM of the FRB, this pipeline, the feature extraction pipeline is running faster, because this is one of the bottleneck which you have for our second part of the pipeline, the post detection. So that we could make significantly faster, as well as you can kind of optimize the feature, which really help us to get this classification going better. So as you can see in this plot, which is actually classified FRB, repeating FRB, and you can see the red one is actually the RFI, and those are actually get through the classifier, and then the blue one is actually the real bus, which is manually a human visualization actually confirm them. And you can see that in the right hand side, when the candies are in operation, you can see the blue bar is kind of getting increased with respect to the rate, which making sure that you are actually really making the classification going positive. And you can actually push the signal to noise ratio limit all the way up to 10, where you say that, okay, you are really kind of reduce the false positives at that point. So that's one of the features which actually really making things different for us. And the fetch is the one of the classifier which was also in the discussion in the talks earlier today. And it is also, we have used the same classifier, but we actually added some optimization there just to make it run faster, especially at the low frequency. And so this is TensorRT is one of the GPU optimization we have implemented, which is basically help to make the thing run faster. And this is an imager, as you say, that we do real-time imaging, so you can clearly see that the data is kind of flowing through the real-time imaging, getting cleaned, and you basically do incoherently dispersed imaging localization of the burst in real time. And also, this part is the pipeline is kind of under development now, which is basically once you make this detection and you actually dump the raw voltages, you really go back and then try to understand the polarimetric profile of that with the incoherent dispersion. And that's what right now the team is trying out to basically look for that how the polarization angle changes with the off-axis sources, and basically we put beams in the different region in the field of view and try to move the source across and see how you can actually retrieve the polarization back. So that is a kind of exercise you are doing to understand these features. And basically, if you do these things properly, then we have a possibility to actually extract the high time resolution polarimetric profile of the detected burst, because this data will be kind of dumped. So some of the interesting results, which is like the system is kind of operational over in full real-time phase since October last year. And as you can see that we actually kind of travel through the number of beams. So we started with 160 beams and then moved to 320, 480. And finally, since last March, we are in the 640 beams. And this part actually you can see, so you have, so these are all kind of commensal detection. So you could see the actually very interesting the solar burst we have seen serendipitously. So the telescope was on sun and you could see a 10 megahertz drifted burst from the solar, which is basically later figured out to be active region of the sun. And then we also see the regular pulses from there, both on axis, off axis. The LPT also has been seen. And these are some of this burst which has been detected by the single pulse pipeline. And then the red line is actually our theoretical detection, theoretical fluence limit, which is almost like 0.2 Jansky millisecond. And we could see the events close to that also during this commissioning and deployment phases. And since this is actually the byproduct of the same pipeline, is also you see in beam periodic sources, and you can see the sky is kind of, these are all the GMRT data which has been seen over the last few cycles, and then color coded by different cycles. And then you can see this all the all the pulsar which you are getting redetected by this pipeline, which is FFA pipe, FFT pipe, and FFA pipe, which is, yeah, we can talk detail later on that. And then so right now also since we have a commensal system, and then you have a beam which is covering the large portion of the sky, and there's a possibility to kind of map all the known sources in the sky. So that's what the new mode we just deployed in last few months, and this is what it shows. So that so here basically what you can see, this one, the yellow dots is the commensal beam from the spotlight, and then the one which is like a kind of sand dotted circle, which basically encircle the incoherent array beam, because we also have an incoherent array beam search going in addition to the post correlation beam. And then the black one is actually kind of map the first null. So we could see sources all the way very close to first null, and given the sensitivity of GMRT, and then whenever there is a source within the first null, within the 10% of the first null, we actually pointed a beam towards that. So we have a kind of internal database repository, which is basically triggering the telescope continuously if there is happen to be any known sources or also in addition, something comes from the external trigger. So through that, we can kind of detecting many pulsar, RRADs, and all the other known sources, all the way up to the first nulls. And also we could actually already deployed a kind of in a framework where basically we kind of triggered based on external things. So right now, based on this, like recently the Chime and DSC are putting their trigger on GCN. So this part we have established. So you basically look for any kind of real-time trigger comes from that. And if it happen to be in the field of view of the current operation, then immediately trigger a beam on that. And also, if it is not, then you basically put in the telescope queuing system so that the earliest possible time you can actually trigger the system to that. So that's based on the external trigger. We also, as I saw in the previous slide, we have an internal database which is triggering the system for. So this is actually one way to kind of increase the productivity of the spotlight. To in addition to having, in addition to get a new detection, you also kind of looking at the possibility to extract serendipitous signs from the existing known sources, since we will be having a very low frequency coverage, which could be sometimes unique for those kind of sources. So you also kind of developing various, in addition to various software processing platforms. Yeah, sorry, Ryan.
If you could wrap up at the next 30 seconds, that would be great.
Sure, thanks, Aaron. Yeah, so you also kind of build up this discovery page to kind of put all the detections there and with various visualization plot, and to kind of finally take the decision like every survey kind of does. So in the summary, we basically wanted to say that, okay, the Spotlight is right now deployed and fully functional, and from last March, like 3 months before, we have a fully working system, and we haven't make any major development after that at kind of stabilizing the system. And then we also have kind of seen the Meniere's detection from that. And just to kind of highlight, so we are working on to increase our ring buffer to kind of basically to make this multi-messenger alert much more effective. And also have kind of having a large amount of in-current array data to basically where you can do a very long period searches. So that's all. Thank you.
Okay.
Maybe time for one quick question. We'll make the next video.
Or you, if there's, I think you can also, since it is online, it may be difficult. So you can write on the Slack. I think team will be happy to kind of discuss on that.
Yes, please, yeah, visible on the slide. I'll make some questions, and yeah, it's good to see you and the team there, and we wish you were good to see you. Okay, thank you guys again, and then I'll take off the next talk.
Okay. Hi, everyone. My name is Mohammed Chamma. I'm a postdoc at McGill University, and I'm also a developer of the Canadian data-intensive astrophysics platform. I would like to talk to you about some spectro-temporal analysis we did recently in 2 recently published papers. Let me see if I can figure out the laser. I cannot. Okay, no problem. So just briefly, our goals are to constrain spectro-temporal correlations between properties of FRBs. We also want to decouple propagation characteristics from the FRB mission. And in doing this, we want to build flexible pipelines for characterizing the FRB morphology. So what we did is we built a pipeline around extracting the arrival times in each frequency channel. So the main steps are shown up here. Okay, so we take the waterfall. Just briefly, I'll go through the steps. We take the waterfall, integrate the time series, fit it with a Gaussian one for each component. That gives us the durations. Then we'll cut out the burst components, which can be complicated if they're blended. But anyway, then we take those cutouts. We'll fit a profile model in each frequency channel, and that will yield arrival times in each frequency. Then we filter those arrival times, and then we can do fits on the arrival time data to get the frequency drift for each subburst and for multiple components. And then on the other side, we can integrate the spectrum with the cutouts, and that will give us the frequency and the bandwidth of the burst. So this is a plot from a burst of August 2023 showing roughly what's going on. This is in one channel. There's the data. We fit our Gaussian model. It's not the best model, but it gives us an arrival time. And there's some statistical information to assess how good it is. We just fit a basic Gaussian, and the arrival time is the 1 over E width of that Gaussian. And then we take the arrival times and we fit this linear model, TR dTd nu times nu plus a fitting constant to get the slope or the segment component drift. So the advantage of doing this approach is you can, it's flexible to the slope model, so you can accommodate strange morphologies, and you can also swap out the profile for something more realistic. So this is an example of the output of the pipeline. So this is data from 121102. This is a microburst. The duration is very short, 4 microseconds. You can see the white points show the arrival times that we get, and then down here in this bottom panel, put a line through it, we get a very small slope or subburst drift. And on the other side, we have a higher signal to noise, so we get a lot more a lot more arrival times. And we can also put in very complicated waterfalls. So this is a Microsoft Forest from Qubit 2023. And it takes some doing, but if you give the pipelines good initial guesses, you can get drifts on each of these components, or many of them at least. Okay, so this is a distribution of burst properties used in our sample. I think there's like half a dozen people in this room who I've asked for data, so thank you over the years if you've been helping out. In terms of frequency, they're well represented below 2 gigahertz, but between 2 and 4, it's a bit of a gap. And then on the duration side, we go down to very short FRBs. And this is a list of the repeaters that we were able to get data for. In general, we use 1 DM per source, and we aim to use the DM of the shortest burst that's available due to its sharp structure. All in all, we get 400 measurements about out of 1,300 total FRB components. So a lot of bursts are excluded mainly due to low signal to noise, which gives high uncertainties. So the sample is ultimately biased to bright, well-resorbed, and well-separated bursts. Much time 3, okay. So our relationship we are particularly interested in is characterizing the slope duration relationship. So under assumptions of a narrowband emission process and some Doppler shift in the FRB source, you can derive a model, you can derive a relationship between the burst duration, shown in the corner over there, and the drift, the TD nu. So that's for each individual component. Yes, okay, so this plot shows the result of those measurements. So yeah, the slope on the y-axis, duration on the x-axis, and the points in the black outlines are single components, and then I've also overlaid white outline points for drifts with multiple components, so the regular drift rate that you're used to thinking about. And then the dashed dot line is the fit to the data from 121102 based on our model, so scaled by that fit parameter A. And we can see for the ultra FRBs, there's only a few points, but they still fall where we expect them to. So these uncertainties, I just want to point out, they don't show the covariance of the DM. So that you can see, like, probably notice that there's a bit of a lot of scattered in the measurements around this line. I'll talk a bit more about that, and you can see the other sources there.
Okay.
Oh, no problem. 2 minutes, okay. Where are we at?
Okay.
Okay. Okay, so let's look at the multiple component drift rates a little more closely. So that's on this left panel here. So what I've done is I've taken out these subbursts, all the subbursts. I've left the dashed dot line from the subburst, and put the multi-component drift rates, and what you see on the lower half of the plot is that it fits fairly well, which is a bit unexpected. And then based on a suggestion from Sophia Sheikh at Citi, who pointed this out to me, she pointed out, oh, well, what happens if you flip the line? Because there's some happy trombones up here, not as many. But we flip the line, and then it's hard, we can't make a conclusion, but it looks like, you know, those happy trombones are where you'd expect them to be based on this line. So that's kind of interesting. So why do the multi-component drift rates and the single component drift rates behave the same way? And why do the positive drift rates behave the same way? Don't know. So just to wrap up quickly, I want to point out some theoretical work done by a PhD candidate, Shwaya Kumar, trying to assess the effect of scattering and dispersion on these relationships. So briefly, there's the case of where scattering dominates, where there is residual dispersion, and where both are present. So you can see on the left we're varying, and note this is d nu dt, so it's split qualities, but there's some fluctuations in the magnitude due to scattering. This crazy feature in the middle is due to a sign flip in the drift. And then when you have both effects, you get both effects. So this could explain a bit of the scatter that we're seeing in the earlier plot I showed. Okay, yeah, so that's about it. I'll leave my summary up, and I'll just point out my collaborators who worked on this. These papers came out in the last year or so, and also the code is available on GitHub. And please feel free to ask me for support if you'd like to use it. Thank you.
I'm sorry. Yeah, so what we basically are arguing is that all the behavior is a propagation, is due to motion in the source. And now sorry, I cannot hear you. I mean, speaking of the software identification, it's essential to define how to be equated to not be forced to not be right. Now, that's software line of the equation about the I apologize, I'm not here. Yeah, that's not.
All right, hello everyone. I'm Sunil Simha, and I feel like a bit of an imposter between all the really, really class So I'll be talking more about FLIMFLAM, or the project that we're working on, but I'll still be
talking about software that we're developing in service of this project. So the idea is that FRBs are probes of the cosmic web, and more importantly, the gas in it. As FRBs come from really distant parts of the universe all the way to us, they propagate through a bunch of free electrons in the host, the cosmic web, and the Milky Way. And depending on, and as a result, they incur this dispersion measure sweep that we observe. Now, despite seeing what is called the McCart relation and then just the DMZ scatter plot, we don't truly understand what fraction of the dispersion measure comes from which component. There's the host contribution, there's galactic halos, the IGM, and basically we want to quantify what the IGM and the halo gas fractions are, which is why we have devised FLIMFLAM. So the idea is that we want to follow up the foreground galaxies along FRB sightlines. So if we have a statistical sample of FRBs with foreground information, we should be able to leverage that foreground information to say something about what fraction of the IGM is, or what fraction of the gas is in the IGM versus the halos. And this was done for 8 sightlines. This is a result from Kirsten et al. This is FLIMFLAM DR1. And we got reasonable constraints on the IGM fraction, although not so great on F-gas. So, of course, we want to make this better, and this is why we're developing FLIMFLAM DR2, which is going to be using more than 50 sightlines. And so that's the kind of data that we're working with. We have 53 FRB sightlines, of which we have 15 with spectroscopic data from the AAT AO spectrograph. 4 of them have Subaru PFS data, and this is one of the sightlines that I'm showing with Subaru PFS. At the bottom here is just galaxy positions in co-moving coordinates shown along the FRB sightline. And over there is what it would look like on sky. So we have a complex tiling strategy with Subaru PFS, which is why you see this sort of hexagonal pattern. We have also supplemented with public data, which is why you see the remainder of the points there. And so with FLIMFLAM, we're starting to probe halos on a wide range of halo masses. So for this FRB sightline, we could see quite a few halos intersect or within 100 or a few hundred kiloparsecs of the FRB sightline in impact parameter. And this is just one sightline, so we have 53 to work with. So stay tuned for what's coming next. So to make sense of the data that we're getting, we are developing various tools. The first thing that we're doing is to come up with this sort of halo gas framework. So previously in DR1, we used a modified NFW profile to model the gas distribution around foreground halos. This was great, but it had a serious flaw in that if you extended the halo gas, the model to larger radii, then it would start diverging. So in order to be more physically motivated and take data from simulations, take inspiration from simulations, we developed this Grapes framework. Basically, if you assume that the baryon mass, the enclosed mass within a certain radius, is some g of y, some g function g times the dark matter profile, then you could basically differentiate this equation, and you can get a general baryon density profile, but as a function of dark matter density profile. And so you get these two terms where the first term is obvious. It's almost like trivial. If g of y were equal to 1, then you're just saying that it's just the dark matter profile scaled by the baryon to dark matter ratio. But then there's this correction term that comes in, and that can be helpful in ensuring the asymptotic behavior that we're supposed to see. So as you go to towards infinity, the enclosed baryon fraction should tend closer to the cosmic average, and that's what this framework achieves. So with this, we're able to incorporate simulation, the data from simulations essentially. So profiles that are inspired by, so in this case, TNG and then Simba. So we can easily plug in these models and test if any of them are inconsistent with what we observe. The other side of FLIMFLAM is to develop this IGM reconstruction framework. And this is work being led by Chenza Dong, who's a PhD student with KG Lee. So he has this very neat algorithm called Mujica, which is a framework to generate constrained density profile realizations. So the idea is that if you have an observation of a tracer particle, so in this case, if we have the field of galaxies along the sightline, we should be able to use that to infer the dark matter density. But the way this works is it first tries to infer the initial condition of the universe that could have led to this galaxy distribution, and then it evolves it consistently with a particle solver. And so you have this lambda CDM infused into this method already. So with this, we're able to produce some density profiles or the IGM density reconstructions for real sightlines. So this is Chenza's attempt at reconstructing 2020-09-06's sightline. So the blue points are FLIMFLAM data galaxies, and the color map shows the mean gas density from this process. So the advantage of this method is that it's a Bayesian framework, so you can produce multiple realizations of this density that are consistent with the galaxy distributions. And as a result, you not only get the average density profile, you also get a standard deviation. So you have an error estimate associated with it. And this is GPU accelerated, so it is very fast. And so within 3 or 40 hours or so, we're able to produce hundreds of realizations of these densities. So we're able to well sample our uncertainties in this method. Sorry? Oh, okay, 30 seconds. Okay. So quickly, I'll just show the inference framework that KG is developing. So stay tuned for his talk for more details about this. But basically, we're able to expand on our on the number of parameters that we're able to use in this analysis framework. And with that, I come to the summary. So with FLIMFLAM, we're trying to infer the baryon fractions in the IGM and in halos. And we have developed a suite of software to help us with that process. So stay tuned for results from us, hopefully by the end of this year. And also look out for talks on day 4 from all these gentlemen who are present in the audience. So talk to them. Yeah, love to talk more.
Great. Okay, thank you. So I'm curious about going forward in terms of samples of FRBs for doing this type of work. Do you think what's the ideal version for which you think?
That's a good question. I think so. It really depends on what parameter you're trying to invert. So if the host galaxy is so there are ideal redshift ranges for various things. So if you have very low redshift, less than redshift 0.1, that's ideal for constraining DMOs essentially. While at the same time, if you have redshift 1 FRBs, then that will be good to constrain DMOs, also IGM. So we'd like to have both.
Yeah, DMOs is good. Any more questions? Okay, yeah, thanks.
Right, thank you.
And
Directions. Direction is always this one. Which one? It's two. Which one is pointer? Pointer is the. Sorry, okay, thank you. Welcome everyone. My name is Marcin Sokolowski. Oh, sure. Mike. Welcome everyone. My name is Marcin Sokolowski, and I would like to start with thanking the organizers for giving me opportunity to present this work. And I will basically continue on what my PhD student Christian Di Pietrantonio was talking about this morning. So he showed the first ever non-targeted detection of low frequency FRB using specifically the NWA, and I will focus a little more on how we actually got there. So a couple of years ago, I initiated a project to develop high time resolution GPU imager for FRB searches, for FRB pulsar and other transient searches. And basically, the idea was to form millisecond images and look for FRBs using interferometric imaging. And so this has been supported. This was so-called under POSI PACER projects, and this has been supported by several institutions, including my current employer, which is Australian SKA Regional Center, OSSRC, and especially also POSI Supercomputer Center, ICRA, Keltin, and UWA as well. So the main goal, as I said, is to form millisecond images like the one shown there of the crab pulsar and detect this kind of dispersive sweeps like from crab. Okay. All right. So as we all know, there hasn't been many low frequency detections so far, but the question is, are they really not there? Or maybe this is because it's really hard, they are really hard to detect. And as Christian was saying, it is very hard to detect them, mainly because of the high dispersive delays, scattering, and things like this, which are challenging and which cause a high computational cost of these searches. So this is something that we wanted to tackle in this process. And our first target was to process 70 observations of pulsar smart survey with the MWA, which MWA is SKA precursor. We used 120 mini stations like this, 16 dipole tiles, and it covers frequency range between 140 to 170 megahertz in this particular survey. Reaches sensitivity of the order of 70 Jansky millisecond, and a couple of years ago, I kind of, assuming that the rates are the same as at higher frequencies, I kind of predicted then in this search, we should be able to detect around 1 FRB. So that's not much, but we tried. So the precursor for this project was actually a project by Susmita Sheth, who was my former PhD student. She used this voltage data from NWA to form 1 second images and look for pulsar candidates, developed methodologies for finding pulsar candidates in images from the 1 second images, basically. Didn't find any new pulsar, but at the time she was using WS clean for imaging, which basically we first, with this Blink pipeline, we first tried to maybe, if we can use the WS clean, but that wouldn't be feasible. Basically processing of 1 second of data in 20 millisecond time resolution, producing 40,000 images would take us probably a couple of days, which we now can process in a couple of minutes. And so with this, why we didn't, so traditionally, and how the MWA group is processing this data is to use tight array beamforming. So they basically cover the field of view with 100,000 beams, and this scales basically like a number of pixels multiplied by number of antennas, whereas interferometric imaging, where you have to do correlation, gridding, and 2D FFT, but you gain that your scaling is also number of pixels, and multiplied by logarithm of this number of pixels divided by by how much you downsample the data. So depending on how these factors compare, imaging can actually be a couple of orders of magnitude more faster than beamforming. So that's what we wanted to do. They both have, imaging has challenged that when you have 256 by 256 images in high time resolution, and you need to form dynamic spectrum of 40 seconds corresponding to dispersive delay at 600, you would need half of terabyte of memory. So this is unfeasible, and we needed to tackle this, which I will try to get later. Both these solutions have challenge of heavy IO operations. So one smart observation is about 60 terabytes of data, so heavy IO operations, but WSClean is much more affected by this because you first need to convert this data to CASA measurement set format. So read it and write multiple times. So that's why we wanted to do it just once. So read the data once, keep in memory, and process this data on GPU. And this is a reasonably well parallelizable problem for GPUs. So that's therefore this solution. So as you can see from this graph, imaging wins by some three orders of magnitude with beamforming for this problem. So and so basically, this is the diagram of our pipeline. So as I said, we want to read these complex voltages just once and then keep them in memory. And we do everything from GPUs. So correlation, gridding, and 2D FFT, everything is on GPU. Then we find we do the dispersion also on GPU, find candidates, and then inspect these candidates later. It's humans mostly. So the other part of this work was Setonics, that we have a supercomputer in paired Setonics, which has a lot of over 700 GPUs, and that's what we wanted to use for this processing. And we wanted to start with smart, but then expand potentially to SKA low. So maybe I don't have much time left, so I briefly highlighted the imaging pipeline itself that was published last year. And this year, Christian created new algorithm to tackle this problem that I mentioned, that we can't keep half terabyte of like dynamic spectra in memory. So what we do is basically we produce images. What we want to achieve is the dispersed time series. So we for every single start time and dispersion measure trial, we produce the dispersed time series from the images we extend this dispersive sweeps using the images that we have available. So as we produce more images, we expand dispersive sweeps, and then once we reach the lower bottom of the frequency, we check for candidates, and we discard, we save candidates, we discard the sweeps to make space for new sweeps. So just briefly summarizing, so this can be compiled on both NVIDIA and AMD GPUs, just in case you wonder. We verified the imager against well-established imagers, CASA, measurement set, Myriad, WSClean. So this is just one example of movie 20 millisecond images. One of our first tests with single pulses from BO950, which should be somewhere around here. Single pulses from this one. That was an easy target. Then the next target, recently we tested on my favorites, one of my favorite source in the galaxy, best FRB simulator in our Galaxy Crab Pulsar. So 20 millisecond image on the left, center candidates, and right you have one example of very bright giant pulse from Crab, dispersion, dynamic spectrum, and dispersive sweep. We detected single pulses from several known pulsars, rediscovered one ARRAT, discovered new pulsar, which actually was maybe not followed up by another group, but was detected earlier. So we just would like to address that once we have candidates, so this we confirm them, and we also have some RFI criteria, especially total power, rejection by total power, and exclusion of bad images with high noise. And we also, on best candidates, we beamform at the with candidate in the beam center, phase center, so that we exclude any aliasing effects and things like this. For example, side lobe detections. And yeah, ultimately, for 7 sigma threshold, we have about couple of candidates from the noise statistic. We would have couple of candidates per hour of observation, 9 sigma candidates, not really. So just for those who were not here this morning, please don't reproduce. This is our first FRB detection. And what I would like to conclude from here is that I will skip this in the interest of time. Okay, I skipped everything now. Okay, so just would like to conclude that the rates, based on our single detection, and the fact that I kind of estimated that if the FRB rates are flat in frequency, constant in frequency, we should see one kind of C1. That basically tells us that the frequency, the rate is not much worse than at higher frequencies, and we should be able to see more of these FRBs. We just need to try harder, I guess, employ the kind of pipeline that we have here. Currently, we can't do real-time cells because we would need a couple of supercomputers, but there is still some space for improvement. So yeah, I'll stop here. Thank you.
And someone will take it one time and say, I think we find something more than no, I would not say a problem with you. Because we only have smart hours, everyone will decide on how we use. So it's not about observation, it's just hours and mile something is how about the project here. So one over the little over 1 hour.
Yeah, my question for you, with your expecting to present a rate estimate, as soon as you have this discovery, but the experience tells us that this typically bias optimistically by a factor of a few. By what factor do you think that? Do you think that the actual rate you expected that calculated before or after the discovery?
Actually, this is in my breakdown from before. But that was for 10 milliseconds of one specific kind of machine. So that estimates were better because it was for 1, 2, or 3. But when we crossed in the end, we ended up with 20 milliseconds research, which has a bit lower sensitivity. So we ended up with my estimates now all the closer. But what is it?
Yeah. The bias typically right. It's kind of that's the bias. That's the yeah. Hey, let's take that Marcin and all because of people. Okay.
Thank you. So I'm really about it. I think everybody got number 5. We could be able to a bit of override the normal session. I'm very honored to discuss a session with Kevin. I think I'm purely radio structural. I'm not engineers. I know still engineering and communication. And thank Kevin for being willing to yeah. Probably it's very timely in especially it's an absolute expert in instrumentation. So we have made several slides. Okay. About how to kick off the topics for discussion. And even though this today there's a lot about the learning progresses, and so that's what amazing. We are amazed by so fantastic reason, but I think the topic should be fixed at on AI use, because that could be much more important for our future, right? Okay. Here's is actually the slides and made by Kevin. We would like to divide several parts and how to run the session in on time in cases.
Yeah, so we tried to plan this in a little bit more in advance, but I learned that
Okay.
very recently.
Yeah,
So I think we're going to try to do it kind of a bit more. And I would just like to ask that when people speak up and have a question or a comment, that they start by stating their name, what university or institution they're at, and also their career stage. So we know that they are a student or a postdoc or more senior than that. And so I think Ray has prepared some facility specific
Okay.
discussion points. That
Yes. Those slides I'll make by myself. Let's begin with the current facility. We can just classify our facility leading testing into two categories. One is segregation. You can find such representative level, for example, fast, variance, GPT, as etc. As I think right now, the most important, importantly, the interferometer play a key role, especially in the FRB post-character as a localization. So China is big, and you are doing a great job on how trigger. And DSA is a very ambitious project, and you're going to localize thousands of FRB. SCAP has done a great job as a pioneer in FRB localization. ECAS is running, and a lot of high redshift FRB has been localized. And yes, there's a lot of interference. And just pick your favorite telescopes in the world. This is a map made by Guiyang, in Guiyang's textbooks. Let's just list the several radio telescopes for FRB search and FRB operation, and it's just the list, not limitation. Then you may think about maybe other telescopes we ignore, but now I want you to scan and do a call and pick your favorite telescopes up to 3. And for Chinese participants to scan the call by WeChat. And if you can go across the Great Firewall using your VPN, for foreign, you can do the slider. I have an open running slider or 833. Do that in 1 minute. Is that okay? This is not very strict survey or something. That's just fun. The right one? The left one, I'm not sure. In the wall. Okay, thank you. Thanks,
okay. I'm not exactly sure what way it had to do with the outcome of this. But I guess I was really excited today to see that there are so many new discoveries being made, like the big pipeline, but that the algorithm and new techniques can actually allow us to get more out of existing facility. So I think we're going to try to have a pretty open discussion about redesign and change planning. Release. Maybe you could give some context as to what we're going to do with this.
Yeah.
This
Let me wait. Okay. The purpose for my tool is following training topics in the internet, and we have a lot of facilities all over the world. And let's just make comparison between each other and just find advantage and disadvantage for your favorite telescope and just make a comparison. For our Chinese people, we never wish our Chinese football national team can be qualified into World Cup. But right now, in the FRB World Cup, it's possible. Faster is very strong, right? Okay, and we never wish this could be a competition. For example, final could be China versus France. That's not our purpose. Right. So let's think about several key questions for the telescope you pick. If you cannot open the QR code, that's fine. Just write a free telescope on the paper, on your desk. Think about this. Actually, 5 questions. Sorry for the wrong number list. 5 questions. What parameter space your favorite telescope can reach? For example, sensitivity. Faster is the most sensitive telescope in the world. The field of view is so cool. How to compete this? And ask that in offline monitor. And you think about the time and the frequency resolution. That determines how you observe and what observing scope you can get, and what bandwidth you need. You have to build ultra wide bandwidth, but that's very that's not easy. Okay. And second question is how to improve the performance capability of your favorite telescope. You can do some instrumentation or do data challenging or commissioning or benchmark your algorithm. The third one is that if you find your instrument is not that good, you may need to equip or buy or develop any other instrument. For example, phase array feed, as wideband receiver, new correlator for interferometry, and new backbone, maybe some HPC class in GPU. The fourth question is that once you can do FRB survey or monitor, you do need multi-wavelength facility to follow up. That's essential for uncovering a progenitor FRB. For example, this afternoon, Huisun has talked about example, and for the SGR 1935, HX70 has observed the X-ray associated with the galactic FRB. That's the huge breakthrough. And you may think about how to use optical telescope to do the same thing. But up to now, we haven't seen any fast optical burst associated with FRB, right? Even GWST or Gemini telescope have built to get this spectrum of the whole galaxy, but that may not be helpful for uncovering the progenitor essentially. Okay, and finally, once you pick, you have come up with a lot of ideas about the 4 questions. You have to estimate the total cost of your instrument. No need to build a new telescope. It's too expensive. Just think about what instrument you need. Okay, here's 5 questions. I may ask if someone would like to be volunteer to discuss about the 5 questions. Please raise your hand. We do not need to do a poll again. It's, the internet here is so cool. I know what you
maybe I'll start by saying that I think if we think creatively that there's lots of space to explore. For instance, these pulse 500s usually have a very low global band of maybe 100 to 200 megahertz. You want to digitize many antennas. So maybe one direction that people think of going is to go to large bandwidths and follow-up instruments and discovery because of those. So maybe others have responses to that or just initial comments. Because I will give us so you agree with that.
With no evidence, and I ask most of them, the VLBI is very
Please say your name and where you are.
Yes, so I'm Marcin Sokolowski, I'm a postdoctoral researcher at the University. And I work primarily with time. And so one of the kind of things that I've talked about previously on this is in the context of estimated load. People often think that estimated load will struggle with the high redshift, sorry, high universal process. Because the dispersion of the sparing attached, the body rate is very important next. FRB is outside the ingredients. I might positive that the low redshift, sorry, the low frequency radiation allows you to observe the higher redshift universe and really know that the interaction rate. And so a very important what you think about is having searches that are exclusively limited to really high linear ranges in order to find something expressed. No, it could be. And that's not something that I've seen in planning for scale low or for instruments that are the more the frequency magnets, which all have factors specific the student officer. Let's bring research to the alcohol 500,000 and look at some students. Which I think is also.
Any responses to Mohammed's suggestion to additional insertion, in particularly low frequency parameters? And by the way, I would suggest that if you have a comment on the previous question, to put two figures up so that we can follow you correctly. And if you have an independent comment, you won't put up one figure. Independent comment from all. Since there's no response from you speak up. This is not is that I will increase significantly. I think it's going to do so and almost it makes it neutral yes by increasing but allows more better estimate. We're going to increase storage. We're going to show there's going to become important. We're going to increase our data probably from the everything up to our capacity. Then we can very easy way search the data and then also try it with your third first machine. So try to use and then we will be new reference and pushing basically. We work, we have more of it, and I think it will also be valuable in other facilities quantify the dollar increase circulation, how they form that levels, because it's not like you guys have no experiences of AOT. It's one of the reasons you get really well. Therefore, I'm sure that your ground concentration, knowing before how you before, this is something that you could explore. Comment on that you should increase data in backend. Will we have a comment? I mean, with that, the challenge which we have in a single dish, for example, in the past, that really saturated more easily. They could a little bit, but on a single dish, so that if you pass that from the place, $500 million, little project isn't that bad. On the other extreme, if you have actual rate and both the extreme for China, when you have the whole element, then and it's stored before reform, you have 1,000 hesitant between the energy speed and reform speed, that is and with 4 bit is better than 2. But I mean, I think it's not that more often that you have to have people like several thousand before you factor in your individual different signals like that. So expensive and for the expensive. with these non-automated chipset. But it actually we can make it.
Yeah, yeah, just as I have, we have one minute. Because we reach a lot of time for the we will also you cover that.
I want to do it in the face-to-face.
Yeah.
Face.
The other comments on that topic are, if not, we can move on to other independent comments. Austin, how about the hospitals? Yes, please.
So, very well, thanks for that. So, we have the capacity to be able to do that. Is that just the case if you are saying the following? We brought more into the passing sources. It would be very helpful specifically.
Okay, we got about 11 now.
Future is, I think it will be very interesting if we survey that. Although the field might not be so large, and maybe you're not having the largest detection rate, but maybe you get a chance to see all kinds of most interesting events like the Yongkun tsunami and the forming region, and also more excitingly like near the supermassive black hole in that center. Thinking that they spent so much hours searching for magnetron neutron star in that center, that it would add on galaxy. But we did find one which is very close to the supermassive black hole. But for all those other galaxies, we were based on and maybe those magnetron in FRBs, but you just have to search in the higher frequency. So even if it's not the maximum rate, maybe it's the most interesting event you can get in the flow, this black hole through this magnetron, and then suddenly around this object, and then it will come to push the receiver in the higher frequency as possible. And also the searching clock will be very low at frequency.
Comments, respond to this, but it's not the other time. This is, this is actually this is right for the phone, no need to come. We searching for the plots and or the CDs. I want to also to actually recently with
Yeah, so the problem at CMD is with 100 people. We were trying to search that with Southwest Telescope. But the problem is that at 100 people, we don't see much dispersion, and also the cosmic ray information is quite bad. So in principle, we expect to find like dozens of also higher data, but to prove that there are these non-trivial. But like if we reach to any data,
and I feel like it's like, but yeah, we're talking about like practice in context of days as well. And for the way in the dispersion files for the searching, you have very expensive more components you have to have before you say what you feel to do. So there's It's not, I think I think to, but yeah, I agree. It's something to, it's something to, you know, be brave.
Yeah, these are smaller activities, and then that we are so proud of our facility because we got back the plan. It's number one of all, actually, but our practice and zero as not that we have to get that by 2019 so serious about why the very system for FRB knowledge for example, many people work with class, Professor Leung, you have any thought about halfway to student class? Yes. Which is with the need with the upcoming grade, the way of using correlation with these correlations. We try to do possible. There are Australians who like to use new tests. I mean, some of my colleagues, you know, they're not. I know you are going to use array in Wuhan, right? Currently, we are supposed to do more so we want to give also staff in our own country. So we want to improve the with our relations of we want to do actually that.
Yeah, so I have a follow-up on how I also have this question of what sensitivity is thought for the way they believe, because I originally expected this to be the thoughts, you know, 64 divisions, each one that's aggregated 3 times under the average. That's so I wonder if it goes to the violence to use the way independently get involved. We have some kind of
what is the sensitivity of the array on the maybe from the last team? Yeah, so student people do price country teaching because we can get closer, just like you can imagine get other bigger data. So that's what we see. And we, astronomers never hasn't been ever satisfied with the fact that you will get everything. Infinity is given as well, full time. And how to reach that? It's many we have to solve.
So also one of the trade-offs here is to have base reviews, like on the then you can kind of hybrid DVD too, if you have if the system is big, and that more you after then meetings. So I feel like I don't understand what the argument is about that.
I have one Casada because like I think this was what found my is how I think it's kind of guy. Everything, but that's not a good idea. It's giving calculate. Total. I think we like to instead of that one, 64 rate with 128 rate. The final would be maybe over 1,000 or 10,000 per rate. That's now the final is simple. And all the case.
The trade-off always around systems. So the example was design. There was a shakedown between system and apps. You have to choose what you're trying to do, but in this case, it shows us we are going to fall. We are more service the pool receives. Somebody's ready to go through. We need to then the pool receives one. Because they're simple. And I was able to then we will figure out what ways we want to do. What I suppose
so I guess then that is the solution Ox is to try what it is about Facebook. What if Ox people want to live on how that has to look?
I think you sort of understand that, the next generation apps will be right, years later, so I think 6 seconds to go. There's also different base rate.
Another comments. I haven't heard how much studies. I feel like a few ways to
Yeah,
and then for universities, where bigger. Oh, so you got to see it. Okay, that's fine. I think that this is very long interview. Maybe we lost from time, and we also see a lot of I think FRB is I haven't seen all from memory data. I think we always we get to realize that two times this problem. And say, one is how using high frequency. Second is high frequency over something so that's so cost is really some deep understanding of things. We can see very not know some users with high extreme capacity. That's not easy to by making small things. So I think we have to be careful of what we can do. So for the currently, we think we probably encourage more small bits of the way because if we see FRB, we see that samples have low frequency, some will be 2 or 3 or 4. We understand in the old world, so also I family is all high. So instrument the ratio, the European or the USA or so there is different style, different text, like small, big text, also big style for this line, the line for the big forming. That's important. So I would say all the cost in my view, monitoring any cost of time, any time is good. So I understand the time is an extremely good example with the IQ and the communities. And really, I will see I think the really great success with my really command. Trying to make sure that such a single instrument GMRT for the region to achieve good results those times. I think the low frequency array like InterJ and I think we all of but I suppose we should see also that we repeat so as a senior person, I think this is happening unexpectedly, right? So we understand that the entire domain, many things, many objects, we have not known yet. We are not really. We should have all mind. Maybe you can see global meeting signal from AGM, from planet, so we there are these findings that we see that they will be from the value. That all velocities is invisible to the time of that. So why do we find the last one to do? We follow what they need of the school study themselves. Second is that we wish that small arrays is easy to be able to go to, right? We start with the space middle ground and take something. You are using again, you are using also in time and to scan all of the people. Then you can and use all the time of the small array to monitor this is real, the data are very but on the other hand, you should always use another class like this. So we have that in your first the very easy to of it. We are based certainly plus minus and so we all these. Okay. So we should probably do sort of try somehow even other people express that in the past. So we can this is what in China nowadays more and so it should be treatable of request. We should not wait. No. Also in the past we said we have whatever values that the local class in the best, let's say, most companies that run from the market. The class should be okay, easy to fit for them 700 megahertz to distribute or so if this situation is on that, we have all of the FRB process, this process, and we do much better than now. So you understand now,
So John mentioned that there are people who identify three base stages. One is light candidate, one is southern sky, and another is observing line where the example of this already happened. Maybe the paradigm that we look at is observing that when we made those first that happened, people might have already today with a narrow observed candidate, we should all but we all the sources is much larger. Anyway, much larger urban time. Or within the base space that not seen, I would might be able to also
all right. Oh, yeah, suppose working. Let me double check. First got 32% votes, and Chime the second. Well, the final could be Chime was so fast. I don't wish that yeah, let's be friends. And let's move on to the next. As you mentioned, as Jingling, Professor Jingling had mentioned, how to find best stuff. How to find anomaly. The best way is to build new telescope, new facility, or completely different department space. For example, Oscar. Yeah, people have never seen that. Oscar. Also, how transient happening in Oscar, and nobody knows. And under such unprecedented time and place, you can expect anything. But that's not easy. SK law is under construction, and finally for SK science mentioning, and you can double check the SK law website. That can be used as an Oscar monitor, just with one station. You do not know all of ambient station. First, really introduce. Yeah, that's great project. But I don't know why you choose frequency with 480 and just follow each time or be part of the time navigator. Yeah, because the frequency is larger than the LF line.
until today.
So the way further 300.
Okay, sorry, my mistake.
And usually they go to behind the road. And from the effective area that where the going up, you lose what power.
Okay, great. Caltech people have proposed two projects for Oscar monitor. One is GX, and another is has. And just you can check the detail in the Leung paper. This is a very familiar project, but in future, as a CSO is building has built space array with a cooling system, so-called cryogenic cooling system. And their dream of, I think would be one of the most ambitious in reduced testosterone, SATA. And unfortunately, this management made it here. And here, people would like to talk about that. That's a dream. But not as I talked to most, and the kids just ignore the total cost. They want to do it step by step to see how far away they can go. Okay. Yes, except for the facility, let's go to the final topic. Maybe we only have 2 minutes. AI for FRB astronomy. AI is a powerful and method you like to use AI. It's a lot of tutorial for teaching time. That's so powerful. But AI, how can AI help our FRB study? As Yongkun, in Yongkun's review talk, he has shown us a lot of fantastic stuff, including his software algorithm called that. Sorry, I missed a letter S. That's very powerful. But other people would like to use AI to do population study, for example, classification of FRB morphology or determining between repeated and non-repeated. Those studies are based on some kind of like algorithm like UMAP. This cluster in machine learning. But the issue is that how can you prove your study as a result physical? And you can find such a dichotomy. Is there any physics you can learn? Nobody knows, right? And in my opinion, I think you can pay more attention to our application using machine learning or using AI. That can be really developed by most of our FRB astronomers, but that's the future. I can remember Evan King is actually talk about the future. If one of the futures are fine, you have to deal with that. The environment can be worse than this. Nobody can stop that. That's with AI, maybe we can find a way to mitigate that side. So this is the final slide, but I just open the topic. If anyone has a source for AI use, especially for FRB science, please let us know.
So I really understand that it's very hard to sort of physics of machine classification. So now I may say still difficult because now we have many observables with measure of fluorescence, variation, cycling, spectral shape, or whatever. So now it's hard to compute to handle all things together. Because machine can help people to classify this data on the fly. And then if we find that some different groups, actually it helps us to find similar groups which have a similar technical properties. Then still it doesn't find this group is apart from physics, but at least we can understand what kind of groups that have properties it is. So in that sense, maybe it's kind of the first there. One and some physics of the power, maybe it's still
I don't know how many patterns, but we still have those physics power. Or independent remarks from students.
How many students doing AI? Your whole there's a lot of posters of AI use. Saying
one going to the developer. And then first comment was maybe.
I think it's so important. I have a question. So looking at graph, we were talking about how their models are against successfully against my last time and we so now being to like search against people for other things. But is there any possibility that actively has like the like FRB classification done in part of AI? Because I know that we're trying to still have our classification done by so I wonder if there's going to be a classification done in part of that.
They are kind of candidates. Someone was speaking at office. You heard them off a lot, so I would do it off the top. So I'm here for you guys. You heard me talk today about how you do good.
is very available. I know I learned from you. AI expert.
Okay. Please introduce yourself, you refer to me, and also
the whole about computers, I could be introduce yourself, but for the whole. Okay, I'm going on our thought. So, in the four, we are the whole part of the world. For example, the whole into operation, search, economy, analysis, how we can use this kind of big model, our data in the writing article publish. So for now, we mostly the AI or the data processing, search, or RMS. Also, some concept of the how we your AI and the black box to describe another black box. So I think we AI can more the physical information on our data or some we are tool to help us to review all the data for us to learn more of the help us to better knowledge. I want to
understand about classes, response to that. I think 1, 2 events a week here. Actually, no, that's the year first. Then we'll go on that. I am not a PhD student in Mali. I have a phone as well as I can use the as you said, the guy and you look at the but I was curious, like, as I didn't try to do, like, some AI writing, but I think that's one step I can still like to get the best time with the relationship call like sign on to the and the second thing was like I would actually use the independent AI classification because then the AI essentially goes to the video or I can and we don't need to or we know all noise. We can understand and we model. Because I saw the AI app to have the video on the TV so that's comments from there. Any confused? Another one. No, just somebody comment. Okay, here's one first. Okay.
So the first slide we use for this is you can probably turn it up, make it mine but not trying to listen to many, so it's not like number of work that we do. And then we still even just this time around that we also include.
Okay, I'm not familiar with the response. Now we go to okay.
I agree that the use of AI is here with black box, but then I have an easy minded black box to whatever extent. Whenever time I was looking at something, there's not, there's no quantification of why someone has an FRB. So I guess in this context, I've been curious with the related comment that you made. Has anyone, Characterizing specifically, while Jayanta, have you tried to use an hospital element model to even picture convey FRB? If so, how would it?
Again, what about more on
My name is Joe. I'm professor from University. I'm using AI in my research. Yeah, I completely agree with the last comment. Because human mind is also that, like, if you make your brand is really nothing, you know, you come out with the correct result. You still have a fact. It's no different from AI. I think AI models are evolving themselves. We still have a lot of like for the entire ability of an AI model. Like we try to create a FRB which will probably will not be able to correct results. So for example, we try to combine maybe a convolutional network with a large number of models, then we will get those higher accuracy, maybe large number of models will probably explain the models of the black box convolutional model. So I think we should try, we should not try to blame the AI black box. We should try to solve the problem, maybe we can try to make AI to explain it.
yes.
So, I'd like to know if there could be a common, there are different developing different classification like the algorithm. And I was thinking if there be a common website that each, for example, has so upload occasionally their raw data and then have all kinds of different algorithms. And then you can compare how many birds they detect with single function and how many like false classification and then and also the certain of facts like so that you can do qualitative comparison of things and people stop reinventing the wheel and know how applicable if this AI code is not for one testing is directly applicable to the other recommendations for a long time. And we have the one platform to have this test that all everyone can do together. This is a proposal.
One of the technical ordinary response that, but we don't really want.
Really? Yeah, so I'm trying to find the purpose of this. Yeah, there is a competitive machine learning platforms, and they have big data sets, I think, more parts, and also all the people who teach a couple of it. I'll find it in my market. Because it is a good help to go on some of the different uses.
Okay. We have as the organizer told me, don't be late.
Don't be too late because everybody is hungry. Okay, this is the final slide. There's no any summary, and I'd like to thank everybody
For joining this section, thank you for your contribution. Thank for all the people who raised their hand. And thank you, Kevin.
Thank you for being with us.
Okay, thank you
all students.
Yeah.
Please
See you tomorrow.
It's not sure we just when you ask them, you don't want to and you don't want to these kinds of jobs they want to
One last issue before the dinner. So somebody we don't have pay for the class wages. So this is the final check. So we will stop the class wages rejection night. So if you haven't payments or you haven't rejection for the tour, you will please go outside and find the rejection table and find one stop to finish one payment. So today is your last check. So yeah. We just
what I was doing. Depends on you. Maybe now. And then the dinner again. So please go to dinner and enjoy life.
어. 差不多了，起来吧。在，应该在。